Have you ever really stopped to think about what's happening inside your phone when you make a call? I mean, it's not just a tiny computer, it's a full-blown, sophisticated two-way radio station, and it's performing an absolutely incredible feat of physics every single second you use it. So let's pull back the curtain and really deconstruct the mind-bending architecture of a cell phone radio.
All right, here's how we're going to break it all down. First, we'll look at the heart of the radio itself. Then we'll get into the single biggest engineering problem that has to solve. After that, we'll explore the two totally opposite jobs it's doing at the same time, dive into some really weird high-frequency physics, and then finally, we'll put the whole blueprint together.
So, let's start our journey right at the core, with the one component that makes all of this wireless magic possible.
Everything, and I mean everything, comes down to this tiny chip called the CMOS RF IC. Now, I know that sounds like a bunch of alphabet soup, but it's pretty simple when you break it down. CMOS just means it's super cheap to make millions of them. RF means it works with radio frequencies, and IC stands for Integrated Circuit, packing a ton of power into a tiny little space. You put those three things together, and you get the engine that powers the biggest electronics market on the planet. Just remarkable.
Okay, but building this little chip presents one massive, fundamental problem. It's a challenge that the entire design we're about to see is built to overcome.
So, here's the question, right? How on earth can your phone listen for this incredibly faint whisper coming from a cell tower that could be miles away, while at the exact same time it's shouting back at full power? Think about that. How is that even possible?
Well, this is what engineers call the Full-Duplex Dilemma. If you don't perfectly separate the part that's talking from the part that's listening, the phone will just be completely deafened by the echo of its own voice. And we're not talking about a small echo. The signal going out is literally billions of times more powerful than the one coming in. It's like trying to hear a pin drop right next to a jet engine. Now, the first line of defense against this is a little component called a duplexer. Just think of it as a really, really fast and precise gatekeeper. It tries to steer your powerful outgoing signal to the antenna and the weak incoming signal to the receiver. But here's the problem. It's not perfect, not even close. Some of that powerful transmit signal always leaks through. And the result? That echo is still overwhelmingly louder than the signal we actually want to hear. So we need a much, much smarter solution.
So, to see how this problem really gets solved, we need to go inside the chip and look at the two very different paths these signals take.
Okay, so on one side, you've got the receive chain, or RX for short. Its entire mission in life is to grab that tiny microscopic whisper out of the air and amplify it with incredible care so it doesn't add any extra noise. And then on the other side, you have the transmit chain, or TX, which does the complete opposite. It takes your voice, turns it into data, and blasts it back out as a powerful radio signal.
This chart does a great job of showing the two key players that sit at either end of the system. First, there's the low-noise amplifier, or LNA. It's the very first thing that weak incoming signal sees. Its challenge is to be super sensitive, but without messing up that delicate signal. Then, all the way at the other end, is the power amplifier, or PA. Its job is to pump out massive amounts of power without overheating. Two totally opposite jobs, but both are absolutely critical.
So how do we finally get rid of that deafening echo? Well, the real genius here is a component called the frequency synthesizer. You can think of it as the orchestra conductor for the whole operation. It tells the receiver, hey, you, listen only on this very specific frequency. And it tells the transmitter, you broadcast on a completely different one. Since they're on different channels, the receiver can just totally ignore the transmitter's loud, leaky signal. But the catch is, the timing has to be absolutely perfect. If it's off by even a tiny bit, you could end up listening to somebody else's phone call.
Okay, so now we have all the parts. We just need to connect them together. And this is where the physics starts to get really, really weird.
See, for the electricity in your house, a wire is just a wire. Simple. But at the super high gigahertz frequencies inside your phone, the speed of light itself starts to become a problem. The signal's moving so fast that it doesn't behave like a steady current anymore. It acts like a wave traveling through a pipe. A simple little wire actually becomes something called a waveguide.
And why does that even matter? It's because of something called impedance. Imagine that wave traveling down the waveguide. When it hits a new component that has a different impedance, it's like an ocean wave smashing into a seawall. A chunk of that wave's energy reflects and bounces backward, creating a brand new echo, but this time it's inside the chip. And these internal echoes, they are a complete disaster. They just bounce back and forth, wasting your precious battery life, and even worse, they totally corrupt the signal you're trying to send or receive. This problem is a showstopper. It absolutely has to be solved.
Luckily, the solution is, well, beautiful in its own way, even if it's crazy hard to pull off. It's called impedance matching. The goal is to get zero reflection, to basically make that seawall totally invisible to the wave. And the only way to do that is to make sure the impedance of the component perfectly matches the impedance of the waveguide it's connected to.
And in the entire world of radio frequency engineering, that magic number is 50 ohms. Seriously, this isn't just some random number, it's the industry standard. It was chosen as the perfect sweet spot, the best engineering compromise between handling the most power and having the least signal loss. So every single part, every wire, every amplifier, every connection is painstakingly engineered to be exactly 50 ohms. It's the universal language that lets all these parts talk to each other without creating those destructive internal echoes. All right, so now let's put all the pieces together and take a look at the final blueprint.
And here it is, the whole system working together. Just follow the signal path with me. It comes in from the antenna and hits the duplexer. That tiny whisper of a received signal gets sent over to the LNA, which is perfectly matched at 50 ohms to capture it cleanly. At the same time, the frequency synthesizer is giving out two different frequencies, telling the receiver to ignore the transmitter. And on the other side, the PA takes your data, pumps it full of power, and sends it out through its own perfectly matched 50 ohm connection. It's like a symphony, with every single component playing its part in perfect harmony.
So what's the big takeaway here? It's that you can't just jump in and start designing the fancy active parts, like the amplifiers. This whole amazing piece of engineering, it's all built on a deep, fundamental understanding of physics, of how waves behave in these tiny high-speed systems. You have to master the physics of the medium before you can even begin to design the components that send the message.
And that kind of leaves you with a final thought, doesn't it? You know, as we push for 6G, for terahertz frequencies, and whatever comes next, the physics is only going to get weirder, more counterintuitive. So, as we keep demanding more and more from these incredible little devices in our pockets, you have to wonder, what new fundamental principles of physics will engineers have to master next to make it all possible?